So, all of that to get to one place, and what's the one place? The formula for that is going to be, whoops. The formula for that is going to be, it's going to be Q enclosed over E naught. That's it. That's your flux formula. New flux formula. And so what we're going to do now is we're going to flip the page over and we're going to calculate flux of various objects. So try number 4. A point charge of 8 microcoulombs is placed at the center of a spherical shell of 15 centimeters. What's the total electric flux through the entire surface for a hemisphere? Does the result depend on radius? And explain. Try that problem. Try the problem. Taking you. Q enclosed, what's the charge enclosed? 8 times 10 to the negative 6. What's E naught? 8.85 times 10 to the negative 12. Yes, put in your calculator equals. That's the flux through the whole entire sphere.
What is the unit? Oh, is it the same unit?
It's the same unit, or I can use the cancellation units over here, right?
Yeah, more okay.
Use the same units then. 8.
What is it? Coulombs per.
It's Newton meters squared per coulomb.
Okay, but if you direct it this way,
I think you have the same thing. You just have to flip and multiply the E naught in the bottom. And I get 904,000 Newton meters squared per coulomb. Is that right? And that's the number of flux lines permeating my space. So how many do I get for a hemisphere?
Half of that.
Half of that. It's symmetric. Everything's legit. I get half of that. How about 452,000 Newton meters squared per coulomb? Getting it? Like this okay?
No.
Come on, Karish, you love it.
Oh, no. Oh, I was answering C.
Oh, you're down to C. Why doesn't it depend on the radius? Explain.
Because the radius is a
Okay. Weak. Give me better. Does it matter how big it is?
No.
The flux lines have to pass through the surface. All of them have to pass through the surface. Doesn't matter how big I draw it. All of them have to pass through that surface somewhere, somehow. Yes, sir.
So, if an electric field like.
Okay, I'm teaching a class, so I'm not talking to you right now.
Okay.
I will happily decide this during nutrition.
If I get a note from Miss the counselor, can I come back?
I'm teaching a class. I don't do these during class time.
Okay.
If she wants to go ahead and put it in without my signature, she can,
Okay.
I guess. But I'd like to talk to you, but not right now. This school is so weird. It's something about not having 40 kids in every class that makes you guys kind of like, hey, while you're not doing anything right now. Good?
Yeah, I mean, you weren't writing anything.
I know. I was paused, and I looked at him like, what are you doing here? So then he felt ready to talk.
But with the electric field,
sit there.
with the electric field, like, does it ever like decay? Like, does the effect get any?
It does decay, because remember, in a bigger area, there's less lines per space. But the total number of lines has to be the same.
Oh.
The electric field is going to go down if you got a bigger sphere, right? Because it's farther away. And there'd be less lines per area. But the number of lines isn't going to change. It's just the area changes.
Okay.
Okay, so far so good? All right, try number 8. Well, I guess it's number 5, but it doesn't have a number on it. Try the 2 charges of 9 microcoulombs and negative 6 microcoulombs are placed in a cube of size 0.3 meters. What is the total electric flux through the cube?
Hold on. We have to add charges.
Q enclosed. We know that positives and negatives cancel each other out, right? Okay, so if a 9 and a 6 enclosed, that's just going to give me 3 times 10 to the negative 6 over E naught.
You're singing the wishes of
Wait, wouldn't it be the same?
So close. So no matter where they're shooting, you're gonna get
Oh, okay.
reflect off. That's why. No, that's
Yeah, I understand. Resmi,
Yes, sir.
it normally makes stuff change. Like if it's odd negative, right? It matters.
It does in this formulation where I'm talking about how the electric field hits something. When I'm just saying how many lines have to go out of the surface, doesn't matter what the shape is, does it? The lines aren't going to, the number of lines can't change.
Okay. So that's why. Thank you.
Right? So we're doing something very strange here because this electric flux is fascinating. It doesn't matter how big the shape is, small the shape is. The number of lines is going to be the same.
What shape the shape is?
The more shape the shape is. As long as it's what? Closed. And that's something you got to watch out for. AP Central loves to ask the question, what if it's not closed? Well, then the answer is, I don't know. It's, some lines get out, some lines don't get in. Done. Right, I don't know. How which way you want to do it? Yeah, there's some lines getting out. Can't help you. Why would you draw that shape? You know better. All right, try the next one. I should require you to actually divide by 6 before you're over.
Oh, spoiler.
No, sorry. Try the next one after B. We did B. We did A and B. That calculates the same for both, right?
Oh, each face of it?
Yeah, now I can divide by 6. So 6, I have 120 microcoulombs divided by E naught, and I get, what do you guys get?
2,260,000.
160,000. Everybody agree with that? Agree with that? For the whole thing, right? So then how do I figure out how much is going through one of the sides? It's symmetric. You should have 6 going, you should have 1 6 going through each side, agreed? So I'm going to divide that by 6. Or to what?
That's squared.
I didn't get that answer, so now I'm really confused. What'd you guys do?
No, oh, no. That was afterwards. That was afterwards.
That was divided by 6. All right, hold on.
The
So-
answer
Final
is
answer.
All right, hold on. Let me 1 3 6 and a whole bunch of zeros. 1 2 3 4 5 zeros. Oh, I need to. I got a problem with the top of there.
That's 13 million.
Yeah. So 13,600,000, and that's how many Newton meters squared per coulomb for the whole entire cube. So that's the answer to B, right?
Yes.
And then A, I'm going to divide that by 6, and that's probably the answer you guys gave me. 2 2 6 1 2 3 4. And so that's how many Newton meters per coulomb go through one of the sides. Now the second question asks, and this is the clever question, this question that's a good one to answer is, does your answers change for A and B if you move the thing closer to one side of the cube? Mr. Nix, what you got for me?
Oh, but the total surface area is the same.
The total surface area is the same,
One face was going to increase.
but the faces are going to be different. So the total number of lines is still going to be the same, right? It's still enclosed, it's still inside the space. This is still going to be the same answer. B is going to be the same. But answer A gets a little tricky because as the thing drifts towards one side, more lines are going to go through here than through the other side. Agreed? Does that make sense? Peter's looking at me. Does that make sense? Okay. So because of that, now, could you calculate that, Peter?
Yes. No.
No, can't calculate that. So if it's not symmetric, that's a problem. We're going to have to think about that as we start to use this law for realsies. Yes, sir?
Dang it. Oh yeah. So if we have a negative charge,
It's just going to be a negative, negative. We've got lines coming
so
in
lines coming in.
instead of out. Notice how it's going to work, right? Remember we had negative charges, lines were coming in, right? And so now you get a negative charge, you're going to have negative answers, and that's going to give you lines coming into the surface, which we said is going to be negative. Lines going out are positive. And we said that when you curl it around, they cancel out as well. So this is kind of a nice feature. It does actually work that way. All right, guys, keep working. These should be pretty easy. I'm approaching the time. Actually, you know what?